Hello, in this video we'll be looking at work and power. Okay, now first of all we'll talk about work. Work is done when a force makes a body move. A body could be something very large, like a car, or it could be something very small, like an electron. So when a force makes something move, now the force is measured in newtons, and it makes something move through a distance, and the distance is measured in meters. These are SI units. These are the units to use in this case. So the definition of work is when a force moves a body through a distance in the direction of the force. Or if you like, once the work is done, complete, you can say the work that has been done, called work done, is equal to the force times the distance, and again I'll say it in the direction of the force. Okay. Now the units, or in fact that'll be newtons times meters, which gives you Newton meters, and also it's the same as joules. Okay, so work done, work is a form of energy transfer. Okay, now let's have a look at a couple of examples. Now the chap who thought of this idea of the concept of work was a guy called Gaspard Gustave de Coriolis, and the idea he had is when an object, and this is developed during the Industrial Revolution, is moved through a height. Now of course an object has a mass, and we have that the weight, which is the force, so this is the force, which is the weight, W there, weight is the force acting down it, when it moves through a distance against gravity, it will do work. And let's say that the work done is equal to force F times distance. And let's say we have a mass of 1 kilogram, and let's say it's moved against gravity 1 meter, so therefore we will have a force is equal to 1 times 10 equals 10 newtons. Okay, and therefore the work done will equal 10 newtons times 1 meter, and so therefore we have the work done, sometimes abbreviated to WD, is equal to 10 joules. So the work done on that mass, when it's moved through a meter, is 10 joules. And that will actually be transferred to gravitational potential energy. It's assuming the mass stops when it gets to the very top. Okay. Another form of work done is when something is dragged across the ground like that. So let's say this is a force, and let's say that force is equal to, say, 1 newton. So if you're dragging something across the ground with 1 newton force, let's say it is moving at constant velocity. Therefore, if a force is being applied in that direction of 1 newton, there must of course be a friction force. The friction force equal to 1 newton. So the work is being done against friction. Now yes, these forces are balanced, there's no acceleration, it's a constant velocity, but there's still work being done because the work is being done against friction, and this is the force. And let's say we move that through, say, 2 meters. the work done will be simply equal to 2 times 1, or rather the other way around. Let's say force times distance equals 1 Newton times 2 meters. Work done is equal to 2 joules. Now let's look at power. Now power is the rate of transfer of energy. And in terms of mechanical work, we could say that is the rate of doing work. Okay? So in fact, power is equal to the work that is done divided by the time that it takes. And work done is in joules, and the time it takes in seconds, so that's joules per second. Or you could think of the rate of transferring energy, so how much energy is transferred in 1 second would give you in joules per second, and is in joules per second or in watts. So power is in watts. Okay. Now let's look at a very quick example of this. Let's say, for instance, we have somebody running up some stairs. This is a classic example. So here are, I'm going to make it nice and easy. 1, 2, 3, 4 steps. Okay, these are 4 steps, and let's say each step is equal to 10 centimeters. So in SI units, 10 centimeters is 0.1 meters in height. That's each step is 0.1 meters height. So the total distance from the bottom to the top, so the distance is equal to 4 steps, 1, 2, 3, 1, 2, 3, 4. 4 times 0.1 meters equals 0.4 meters. So the height there is 0.4 meters. Now let's say we had a chap here. Rather big steps, aren't they? Heavens. Or a rather small chap. Draw a bigger chap. Okay. He is going to run up those stairs. Now, what is he working against? Well, he's working against gravity. Gravity is working against him, and so therefore we're assuming he's working against gravity. So the force in this case is going to be his weight. And let's say this chap is 70 kilograms, and therefore his weight, the weight acting down on him, the force which is happening is 700 newtons. That is 70 times 10. So here this chap is, he's going to run up the steps. And so what is the power? What is the power he develops? Now power is equal to work done, which is force times distance, divided by time. So what's the power? We don't know the power. We can't calculate it until we know how quickly he does it. Let's say he runs up those steps in, I don't know, say 4 seconds. Okay. It's pretty slow actually, 4 seconds. More dawdles up it. So let's say he gets to the top of those stairs in 4 seconds. What is the power he develops? So I'm just give some space and write down what we know. So we know that this height here is 0.4 meters. We know that the force, which is his weight, is equal to 700 newtons, and we know the time he's going to do it. I said it was 4 seconds. So the power that he develops is force times distance, F times distance, work done divided by time, which is 700 times 0.4 divided by 4, and I believe that will come out as 70 watts. So he develops a power of 70 watts. So every second he will transfer 70 joules of energy into doing work moving against gravity.